Hello everyone, I'm Hemanth. I am here to present my view on 14-day internship on real-time EV dashboard and ADAS. So let me start the presentation. I joined this internship to learn about embedded systems and real-time hands-on experience. As the as I every day participate in the internship, I learned so many things and I have realized there is so much to learn in the embedded systems, and I am very excited to present this slide. Okay, first of all, on the day 1 and 2, the instructors have gave us the overview of the project what we are going to working on and familiarized us with the softwares like STM32 and PiximLab. STM32 is a IDE software in which we are going to write the code, and PiximLab is the simulator in which we are gonna see the output. On the first and second day, we are the first and second day we write a blinking LED program and used a toggle function to blink the LED. On day 2, we are we created a zero dependency GPIO register, writes and toggle the active low onboard LEDs as a base pipeline verification. On day 3, we have worked on ADC. ADC means analog to digital converter. In this ADC is used to read the analog inputs and convert them into digital discrete signals. So we have used a 12-bit ADC, which means in we have used 4 ADC, only one ADC, 4 ADC, one ADC with pins from the STM32, PA0, PA1, PA2, and PA3. The PA0 is connected to the accelerator pedal, which gives the output from 0.1000 to 3.3 volts. These these voltages are converted into discrete format by 0 to 4095 values. That means the greatest value 3.3 is gonna represent in digital like 4095, and the least value is 200 is 0, and the middle value will be between the 0 to 4095. And the brake pedal is also similar. We can adjust the brake pedal and any pedal in the analog ADC device to get the digital output. And the next day we worked on the ultrasonic sensor. An ultrasonic sensor is used to detect how much distance it detects ultrasonic waves from one. It sends ultrasonic waves from trigger pin and receives it from another pin called echo. By transmitting and receiving of the same signal from the trigger and echo, it can calculate the distance. We used HCSR04 sensor, which is an ultrasonic sensor, and used PB0 terminal to operate the ultrasonic sensor. And we used the timer 2 to calculate the time taken for the signal to reach the echo pin. And we also write the code for a single ultrasonic sensor in the IDE interface and simulated it in Pixim lab. Okay, and the very next day we worked on timers and hardware interrupts. Timers are the heart of the any microcontroller. Without a timer, we can't do anything. The timer is used in ultrasonics and also to get the precise values. For suppose if a EV vehicle is traveling with a constant speed and there is a vehicle in front of it, the ultrasonic will only detect the correct measurement if the timers precisely work. If the timers are not precise, the collision cannot be detected and we may get into accidents. Okay. In hardware clock configuration, the timer works if we give the timer works as the timer works as a timer when we given clock signal to it. We have given 72 megahertz signal and pre-scaled it to 1 megahertz by dividing it by 71 megahertz plus 1. 71 plus 1 and pre-scaled it to 1 megahertz. After that, we designed a non-blocking interrupt hardware architecture and programmed timer 1 to drive EV vehicle dynamic solver at 100 Hz, that is 10 millisecond loop, while setting timer 3 to trigger ultrasonic loops at steady 10 Hz rate. Okay, on day 6, we have worked on EV controller mechanics. In EV controller mechanics, we used formulas on inertia physics model developed by dynamic state equations in evcontrol.c to track the motor torque, drag, coefficients, battery range, approximation, optimized derivation torque and mapped based on the driver configuration. Instead of using a dummy number, we implemented a real-world mass inertia model. The driver throttle position torque to 60%, normal at 100%, or sport, which boost up to 130%. The brake pedal is pressed greater than 5% threshold, then the motor applies negative torque to create negative torque to minus 80 Newton meter, exceeding the regenerative braking and converting the SOC back into energy accumulator. In day 7, vehicle finite state machines, and I on the day 7 I created vehicle finite state machine. A secure EV cannot be operated in a single continuous loop. It must navigate defined safe operational states. We designed 5 states: parked, ready, driving, regen, and fault. For example, vehicle cannot enter driving state unless FSM has verified ready checks and throttle travel is detected. If a system fault is detected in any state, the state machine triggers an immediate deterministic jump to fault state, which immediately halts motor PWM signal to guarantee passenger safety. On the day 8, we worked on ADAS engine calibration. We all know what is ADAS. ADAS is Advanced Driving Assistant System. We don't just measure absolute distance, we compute time to collision. Time to collision is the time before colliding with the other vehicle. If the time to collision, if the measure, the distance read from the ultrasonic sensor is less than 30 centimeters, the time to condition, the time to collision is very critical, and it returns a critical indication and with a warning on the dashboard and also blinking LED red, which will we be seeing on the dashboard later. To prevent rapid and annoying alarm toggling near the threshold limits, we implemented 300 millisecond temporal hysteresis filter. We trigger a warning alarm if an obstacle with 50 centimeter or the TTC is under 3 seconds, escalating a critical emergency alarm at less than 20 centimeter or TTC under 1.5 seconds. For blind spot monitoring on the side sensors, we apply a speed gate so the alarm is only active about 20 km per hour. Going to next slide. Fault system unmanaged. On 9th day, we implemented the diagnostic fault manager. We created a modular bitmask architecture in fault.c. Fault.c is another source file source file which we created to make the program easier to understand and easy to implement. Okay. To monitor safety critical parameters, the system continuously evaluates motor temperature against 120 degrees Celsius thermal limit, battery charge against a 5% low voltage cutoff, and the ADAS line for critical collision warning. If any of these boundaries are crossed, the diagnostic center bit is set. The fault manager immediately overrides the system and forces the FSM to fault state, shut down the motor drive and illuminates a physical yellow diagnostic LED which is connected to pin B11. On the day 10, we worked on diagnostic serial shell. In shell, there are two files, um, shell uart_shell.c and uart_shell.h. In C file, C is a source file in which we write the code that controls the UART, and in H and in header file which is having a .h extension, we write the headers required to implement the UART. The UART USAT run which runs at 115 and 1200 bits baud to prevent serial processing from delaying our 10 millisecond safety critical motor loops. We configured direct memory access to receive data into circular ring buffer without CPU intervention. We also developed a command parser that reads the input like status, speed set, fault clear. This mimics the standard interference used in workshops, diagnostics, enabling developers to monitor system values and interfere enabling to monitor system values or intentionally injects faults to test our safety isolation routines. On the next day, we implemented the Python telemetry pipeline. In this, on this day, we created a dashboard which consists of all the parameters like SOC, which is state of charge, time to collision, brake, brake pedaling, acceleration, and blind spot to left and blind spot to the right, front distance, and also bird's eye view for the representation and to visually see how our project works. On this day, we also worked on UART to connect the Pixim simulator to the Python dashboard with the use of VSPE tool, in which we use COM1 and COM4 for communication between the Bluepill, Bluepill, which is a microcontroller used in Pixim, to the dashboard in the Python. On the 12th day, bird eye view, ADAS and display. Our data visualization into a Tesla style dark dashboard. The UI features ADAS bird eye view panel displaying an overhead graphic of our vehicle surrounding by dynamic obstacle arcs. As obstacles approach, the UI maps front left distances and shifting color zones instantly. Green for clear, amber for warning, and red for critical limits. If fault occurs, the dashboard displays a full width warning banner. We verified our pipeline delay from moving slider in PiximLab, processing in STM32 and rendering on screens, remaining under 150 milliseconds. On next day, system validation testing. I executed the full system validation queue, running 17 target test cases. We verified correct ADC scaling across all the channels and tested the alarm hysteresis limits by toggling obstacles directly around 50 centimeter boundary to ensure the indicators did not chatter, and ran a comprehensive UART packet integrity test, achieving zero CRC dropouts over 1000 transmitted packets. We also tested edge cases such as physically disconnecting an echo pin to ensure the system fell back to a safe 400 centimeter limit rather than scaling the microcontroller. The final day, submission and review. I, com- I compiled the final day. I compiled the final project to maintain production gate design principles. I ensured the code bases remain strictly modular. EVcontrol.c manages only vehicle physics. ADAS.c runs risk assessment. Ultrasonic.c isolate low level timer capture, and fault.c act as our central interlock safety system. We packaged our verified STM32 firmware, the Python HMI dashboard simulator configuration files, and testing reports into our final submission. I am proud to report that 100% of our architectural deliverables are complete and passing. In conclusion, in summary, we have built a fully functional deterministic EV ADAS warning system. The codebase cleanly separates hardware abstraction, physics modeling, risk assessment, and diagnostic communication, meeting 100% of our architectural goals and providing a solid foundation for real-world automation ECU development. Thank you. I would like to thank my sincere gratitude to the entire team at EMERTXE Information Technologies for designing such a comprehensive and industry relevant embedded system internship program. I am deeply thankful to instructors and mentors for their step by step guidance, clear conceptual breakdowns, and continuous administrative support. This 14-day hands-on experience has significantly bridged the gap between my academic foundation and real-world automotive firmware. Okay, that's it for this slide. Now we see the working of the project. First, we should open the IDE. This is the main.c file. Yes, it is the main.c file in which we have written the code, and these are the EV control H contains the header files for the controlling of the EV electric vehicle, and fault.h and fault.c for the ADAS collision, blind spot right and blind spot left, and speed control, torque, temperature, SOC, etc. Now, first we should build the project. Build project. Here we get zero errors and zero warning. Next, we should open Pixim Lab. Open the file. Load the binary file ev.bin, and open file again. Configure and put the serial port at COM4 and save. Okay, now open the modules, spare parts. Now we can see the ultrasonic sensors and potentiometers. Okay, okay. We can also see the output in virtual terminal first. Sorry, the virtual terminal is not set. It will take it time. So here you can see the output. I changed I changed the baud rate so I can observe the output in the virtual terminal. So here front distance is 14 and left distance is 196 and right distance, which are blind spot 290, and TTC, which is time to collision, is zero point 0, and BSD, which is blind spot, sorry, BSD alarm, and FLT, which is fault. Fault is 0, which means we should increase the front distance to avoid. Here the red LED is for collision and the yellow is for fault. So our fault is 0 here. Now let us build the IoT dashboard. First of all, we should open this software, which is BSPE, which is already active. Okay, now we should open command prompt. Okay, I should be opening the Here I'm trying to open my file. Here I'm going to run the dashboard. The Python dashboard takes time, so please wait. Where is dashboard? Yeah, run the from the program. It should activate anytime. So where is it? Yeah, the we can see the Python dashboard. I will maximize my screen. Here, where is it? Okay, here using the accelerator pedal, I can increase my speed, and using the brake pedal, I can decrease my speed. And when I apply brakes, it should slow down. Yeah, you can see, you can clearly see when I decrease the brake pedal, it gradually decreasing from 90 kilometers to the 85, 86, and so on. And I will increase the accelerator slowly, then it will rise. Okay, it will take time to increase its speed. Now I will decrease the front distance. We can clearly see there's a collision warning. Let us see in the dashboard. Here it is advisory. The EV vehicle is less than the 20 centimeters to the other vehicle in front of it. Now we can change the front distance, and the red LED has stopped glowing. Now we can see the alarm is none, and we can also change the blind spots, which are increase or decrease. This is the left right blind spot, and it's the left blind spot. If I increase the motor temperature, it will show you. Yeah, it's showing the motor temperature 59.7, and the time to collision is 0.1. Okay, it's the bird eye view. It's the front distance. It's the left and it's the right. We should slow down the accelerator for not colliding with the vehicle. The alarm says advisory, and the motor temperature is rising. The accelerator pedal is dropping to 44, 43. If I put the accelerator 0 and brake to 100, it will stop. So the input is not, it's not taking input. Okay, this is the dashboard, and thank you for emerging internship for the 14-day free internship, and thank you very much our mentor and our instructor.